Hey everybody, let's back to the second part of this tutorial. Welcome again to the tutorial session number 1, which is entitled Training Deep Neural Networks, or Training Deep Networks from Zero to Hero. My name is Sandra, I'm professor in the Institute of Computing at the University of Campinas, and today I'm going to be the chair of these sessions. Just let me remind you to ask your question on YouTube chat on your Discord channel. So let's invite our speakers, and the stage is yours. I think now it's up to Fernando. Yeah? Fernando, are you here?
Yes.
Yes.
Hi.
Okay.
Hi.
Thank you, Fernando.
Okay. Thank you. Thank you, Sandra. Hello. I will continue the tutorial now. Training deep networks from zero to hero. In the morning, Moacir, Leo, and Gabriel talk a little about the some issues when we train the deep networks, some units that we can put in the structure of the networks. And now we're going to see how we can use the networks to operate feature extraction, to perform fine tuning, and how we can advance and use some recent techniques to improve even more the training of networks. All right. So I will talk a little about the concepts of transfer learning. Also, a little about the feature extraction using deep networks pre-trained, how to perform fine tuning, and also advanced technique curricular learning. All right. All the presentations and the codes we are showing here, you can get in this link. All right. Good. So we have some definitions about transfer learning. The two more used are the first one. Transfer learn is the improvement of learning in a new task through the transfer of knowledge from a related task that has already been learned. And the second one, transfer learn and domain adaptation, refer to the situation where what has been learned in one set can be exploited to improve generalization in another set. So what we want to, when we apply transfer learning, is to reuse some knowledge that we already have and try to improve the learning task and the current moment. So we already know some use of learning that we achieved in the previous task, and we want to take this learning to facilitate a new task learning. All right. And we can perform transfer learn using deep networks. So we can use pre-training network and operate feature extraction and use the feature space and some external classifier. We can perform fine tuning, and we can also use transform these features and to our current task. So a briefly definition of transfer learning, we need to have a domain which is composed by a feature space and a probabilistic distribution. And also we have some task, which we want to use a prediction function to obtain a label space. So in the transfer learning context, we want to use all the knowledge in the source domain or the knowledge in the source task to improve them the curved task here. So before we actually enter in the transfer learning aspects for deep networks, how a regular approach for deep networks really works. Uh, the first, we needed to design its topology, right? So we needed to structure our network, choosing which units we can put in. Some, for example, convolution units, pooling, dense, and others. Then we can need to define its training strategies, choose optimizer, the loss function, some measure, and then render initialize all parameters. And then we can train the network from scratch. All these topics here was discussed in the morning. We see some kinds of the units, some kind of training strategies, and now we can advance here and talk a little more for how we can use some pre-training model that we already have and use this for our feature extraction or fine tuning, right? So the regular approach involves we have a lot of data, and some cases we don't have this amount of data. So we have a very small data set. We can use pre-training models and use this model as feature extraction. If we have a little more data, we can load some pre-training model and then fine-tune this model for the current task. So when you want to execute feature extraction, we can have some points to consider here. The first one is to choose the desired pre-trained network. So we have a CNN, for example, that we already have the weights founded by the pre-training, and we use our data set and pass this data through the pre-training CNN and obtain a feature map. For to obtain the feature map, we need to choose which layer is going to be used as feature extraction. So for example, we can choose the prediction layer. It's very common to use because this layer, it's a combination of all the previous layers in the architecture. So with the feature map in hand, we can choose any external classifier and obtain, for example, accuracy. This methodology here can be explored in several manners. For example, we can choose to apply some dimensional reduction technique to reduce the number of features that we obtain in the feature extraction process. We also can combine different features maps. So in this pipeline here, we choose two different layers to provide two different feature maps, and we can combine these feature maps by operating fusion and other different manners, and then use an external classifier. Note that this pipeline is very useful for us when we have very little data that we don't can possible train the structure there. This methodology is very useful for us. I will show you a notebook for this process here. For example, here I just import some libraries in the Python, and so just for our example is to be more faster, I add this function here to select P% of the data. Here I choose only 5%. But in the real application, we want to use more data, right? So here I load the CIFAR dataset. Moacir told us some problems with these datasets in the morning. Problems related to the actual label from some examples, but it's very useful for us. This dataset is very common benchmark. All right. So I load the ResNet 50, a common and very used CNN. I load this model with the weights from ImageNet, with all the input shape and the 1000 classes at the top. And I want to get this model and select a different output, right? So the original output is the 1000 class. So when I perform, I select a different output, I am changing, throw away the prediction layer. So I want my new model to have the same input, but the prediction output layer here. So I can pass all my training data and test data to this model and obtain a feature space for training and for test. With the feature space, we can perform a different operations. We can perform a dimensionality reduction. We can perform a features fusion, even apply a different transfer learn techniques. And then, if the result feature space, we can actually apply the classifier here. For example, support vector machine. So this implementation gives us a direction in how to use pre-training models only for feature extraction. All right. So this is the first applying for pre-training models. The second one, it's about fine-tuning network. If we have a bit more data from this very little training set, we can apply fine-tuning. If we have a very large data set, we can train the architecture from scratch. But fine-tuning as a resource, very useful for us when we have some data. It's not large, but even and also not too small. So fine-tuning consists of reusing weights from pre-training network with large data sets and refine the solution by training the model with the current data set task. All right. So here we have a pre-training network, for example, trained with ImageNet. So we have several layers and prediction layer here. And we can copy all these weights and change the prediction layer for our current task. So if we have a data set with 10 classes, the prediction layer will be 10 outputs. Okay, so we can also change some mid-level layers here. We can choose which layer we can change and choose how to train the network. We have some issues that we may pay attention when we are performing fine-tuning network. The first one, it's about resolution. If we have some images, for example, with low, if tiny resolution, we might need to increase the resolution and consequently add some noise. On the other hand, if we reduce the resolution, we may lose information. So we need to pay attention and study the context of the data set before choose which way we're gonna to use. Another issue that we have to pay attention is to ensure representativity, increasing the train set. We can apply some data augmentation methods. We can choose a similar domain with the same classes and then increase the amount of data then going to be used in the training. And also, we needed to choose how to to update the weights. We can choose to propagation, where all the weights from the previous training can be changed by the new training, or choose some layers to be frozen. Then only a few layers in the end of the network can be updated in fact. I also have here a notebook for fine tuning, and I'm going to use the same data set, CIFAR, and note that the ResNet, the original ResNet, have 224 pixels resolution for inputs, and our CIFAR dataset have only 32 pixel resolution. So we needed to increase the all these images for to use in fact the ResNet. Of course, here we are only show implementation that you can adapt for your current task. All right. So I just want to remove the prediction layer. Then my new model have the original input and the pre-prediction output. Then I want to add a new prediction layer. So I create here a dense layer with the number of classes. The output is the number of classes for my data set. All right. So I can choose once more how to compile this model, the loss function, optimizer, the measures, and my new architecture are ready to be trained. So here we can train our model with some parameters, a number of epochs, the batch size, and we have the model fine-tuned. Okay, here only for example, I choose 10 epochs, but of course, we need much more epochs for adapt the network to the current task. Just one observation here. If you use these parts of the code, we can froze some layers. The first layers is not going to be updated. So for this example here, I only allowed the last 10 layers to be updated. So the first ones is going to be freeze. All right, so here we have the training loss and the accuracy for only 10 epochs. And then we can test the model using the test set, right? So we have aquí some accuracy for this model here. All right. So when we have small data sets, we can choose between feature extraction and choosing some layers to obtain a feature map and choose an external classifier, or even choose operate fine tuning, choosing some how to train again the network, choosing how we going to which loss function, optimizer, if we wanted to allow some layers to be updated or not, and test the model again. Okay, so here we have some tasks that we can perform. But if we want to train the network or even perform fine-tuning, we can choose some advanced techniques. Yeah? We can change how we perform fine-tuning. We can change how we perform the training from scratch. One of these techniques is curricular learning. Curricular learning, it's the same idea that we all pass in school, for example. The teacher choose which subject is more easy to learn, then we learn the easiest first. So we learn how to operate the sum of two numbers before the multiplication, for example. And for deep learn, for deep networks, we can apply the same idea, offering to the network the easiest examples to be learning before the most difficult ones. So curricular learning is based methodology to choose how the data is offered to the training to train the network. Some definition. So curricular learn is an advanced training strategy based on the concept of learning instances considered simpler before more difficult instances. For example, here we have two pictures of bears and two of horses. Consider only the images of bear. We can see, for example, that this picture has some occlusion that can be more hard to learn that this animal is a bear than for this picture here. For the horses, we can observe that the second photo have some multiple objects. Then it's more difficult to learn that we have horses here than in this first picture. All right. When we are applying curricular learning, we have to decide two functions. we need to decide how to define a scoring function and also a pacing function. The scoring function is a metric to sort the training example from the easiest to the most difficult one. So we need to have some methodology to assign the degree of difficulty for each example, and then sort the training set according to their degree of difficulty. In the literature, we have two basic scoring functions. The first one, transfer scoring function, that we can extract features using some pre-trained CNN for the training set, and use this feature vector for prediction in an external classifier, getting the score for each instance for the respective label. Then, with the score for each example, it can sort the instance according to this difficulty. Another scoring function is self-taught, where we train our network from scratch during few epochs, and then we can use the same training set to predict and get the score for each instance. All right, and once more, we need to sort the instance according. We can observe here that we are not training the network. In fact, we only prepare the data for the actual training of the network. We also need to choose some pace function. Pace function dictates the learning speed to incorporate more examples into the training set. So for example, we can choose some linear pacing function, and for each epoch, we increase the amount of the data to train the network. We can choose some log pace function, a ladder space function. We can explore these functions and see how our data sets behave during the training of the network. When we consider a score function as a random measurement and a constant pacing function, we have the conventional training of the network. So here in the blue line, all the data is offered to the network, and we do not measure if one example is more easy or not to be learning than the others. So when you use a constant and a random measurement, we apply the conventional training of the network. I also have here a notebook to implement this idea. So here I use the same data set, CFAR, but now I not use a pre-trained network. I will build my own network. So here we have 3 blocks with two convolutional layers and average pooling. And the final of the network, we have 2 dense layers. And the last one with the number of classes from CFAR. Then I compile this model, use some loss function, optimizer, accuracy as a measure. Then we have the structure of our model. Now you define the scoring function, where I pass as parameter the training data, all right? And I train this model for a few epochs, 1% of epochs here. Then I can predict the same data used to train only to obtain the score for each example, and then sorted all this data. So when I return the data from the scoring function, we have the training data sorted by difficulty level. All right, so it can, after this, and defining the pacing function, you define how much data we're going to use during the training. I also define a pacing function here. So we have a linear pacing function, logging, ladder. Note that when we are using the ladder pacing function, we needed to establish how many steps you have. When we saw the graphic, we can note that for during some set of epochs, the number of data is the same. All right. An important consideration here is to maintain the training data balanced. So this routine here, it's only to select the same number of the data for each label. All right. You can improve the code to do this routine more faster after. Then we have actually the training process for the model. So I needed to verify which pace function we are using, and the pacing function here will return for us the amount of data we need for this epoch. If we are not use a different pace function from constant, if you are using the constant pace function, we only have to use all the data for this epoch. And then we can actually train the model. So for example here, executing all these functions, first we have the scoring function, where we train the model for a few epochs and define the difficulty level, sorting the instance, and then training actually the model. We using a ladder pace function here. So we can note that we have some accuracy for the training, accuracy for the test, and the loss here. But note that for the first epochs, we have a small number of data, and then when we increase the epochs, they also increase the number of data used to perform the deep network training. All right. We need to also pay attention for some considerations when you apply curricular learning. We already have some dynamic functions that measure the degree of difficulty during the network training. For example, the score for some instance can change his level of difficulty during the network training. So you already have some dynamic functions that change the sort of the data during the network property training. Okay, right? Another concern is to keep the training set balanced. We have several studies that measure the influence of this balanced data sets. And also, several studies show us that setting the learning rate wrongly can cause a training performance degradation. So the result can be even worse than conventional training. So when you apply Coherently Learn, we need to pay attention to keep the training set balanced and explore different learning rates to obtain the maximum of the performance. Another interest topic is that we can apply curricular learning for tasks. So the easiest task must be performed before the most difficult ones. Another example is that simple loss functions can be used to start the training for a deep network, and then we can choose another more complex loss function and retrain the network. So for one example here, we can build an autoencoder to only initialize the weights before we actually apply the supervised learning. Even when we are performing the conventional fine-tuning, we are using the idea of curricular learning. So we use a pre-trained network. We already have the weights established, and then we can apply the fine-tuning to more complex scenario. It's more small data, and then change the last layer. So it's kind of the idea of the curricular learning also. For this scenario, we have here some example. We can build some autoencoder, all right, and train use, for example, for all data, and then separate only the encoder part and add some dense layer in the final and apply fine tuning to reusing these weights to refine our solution for a supervised learning, for example. All right, this is very useful for us because if you have some training data with partial labeled and partial unlabeled, we can build the autoencoder and train it using the old data, and then apply the fine tuning only for the data that actually have the label. So we cannot discard the old data only because we want to operate a supervised learning. Okay, so let's see an example of implementation for this scenario here. Once more, I use the CIFAR dataset, and I prepare my autoencoder. So here we have some two convolutional layers, max pooling, and a flattening unit to characterize the code. And then our decoder reshaping, upsampling, and transpose convolution. And then we choose some loss function, optimizer, and then we have our structure here. All right, so we have the encoder and then the decoder. I'm going to train this autoencoder here using my training data set for a few epochs. And then we have here the loss, the result for the loss function. Then we can use the same idea of fine-tuning. We apply the idea of curricular learning for different tasks, and then I select the input of autoencoder, and now the output will be the code layer that we separate the encoder from the decoder, and add some dense layer in the final of the architecture with the number of classes from CFAR. And here the process is the same for the fine tuning. Basically, we can choose the optimizer, the loss function, some measure, and apply the training for this new architecture. So here we have our CNN. It's few units. It's not a deep network properly, but we can see the performance here for the loss of the data, right? Of course, we need to study the data set, study the units that we wanted to use, if we need to apply data augmentation techniques. But these 4 codes here, it's an example of implementation that we can use it to improve our models, changing some parameters, increase the depth of the network, and so on. Right? To sum up, we saw how to perform feature extraction, how to perform fine-tuning, and how to apply the curricular learning. I want to let for you some complementary readings. This first one, which also has authors Moacir and Leo. The second paper here, it's a survey on transfer learning. The third paper, it's all about fine-tuning, all right? And the last 2, it's about the curricular learning. And the curricular learning was published here in 2009, and 1-2 years ago, it come back here. It's more deep study about this technique. All right, we have time for some questions, I guess.
And I have a quick question for you.
Okay.
In which situation do you think is it better to train from scratch than from fine-tune or transfer learning? Do you have this situation?
We usually use training from scratch when you have a lot of data, right? If you have a small data set or a very few data per class, we need to, it's better to perform fine-tuning, even apply some data augmentation techniques to improve the increase the data set. And curricular learning is a good idea when we have this difference between the images. So we have some images that we have the animal, for example, and the different perspectives, some occlusions. Then we can try to improve the convergence, apply this technique, separate the most easy ones from the most difficult ones.
Nice, thank you.
All right.
So I think you can call the Leo. Leo, are you here? Okay, the next one. Okay,
Hello.
nice. Thank you, Leo.
Thank
Thank
you.
you again.
Yes. Okay, so I'll be talking about contrastive learning for you to achieve better representations, which I guess is something everyone wants. Okay, so we'll cover here the idea of representation, which Mosseri covered a bit before. And we'll talk about contrastive loss, triplet loss, that's a custom version, I don't know. And we'll try to get some coding time in on time this time. I even have a stopwatch this time. Yeah? Okay. So you have seen this pipeline this morning. So this is just the traditional machine learning pipeline where your images go through some pre-processing, and then you have a feature extraction, and that can be like color features or shape features or some more complex ones like sift and surf. And then you have your task. I'm listing a classifier here like multi-layer perceptron or an SVM. And then we got into the deep learning era, I guess. And now the whole network is both a feature extraction bit and that it's trained to do the tasks directly, right? Because we don't have to think about extracting color anymore because we expect those huge networks to learn the necessary features by themselves. And this idea that the network is capable of extracting features and that we can use these features as like a space and do other things with it is called representation learning, as Benjo and friends called it on their book, the deep learning book. Yeah, so what I want to talk about is how do we specifically learn for representations here? Because it's very useful going beyond classification and beyond end tasks. Just teaching the network to create good spaces allows us to do content-based image retrieval, pre-training for multitask features that will come later, recommendation systems. YouTube, I know, uses a contrastive learning thing to do their recommendation system. Face recognition, which no one should do really, but you know it exists. Unsupervised learning and self-supervised learning, which Gabriel will cover right after the break after me. Yeah. So specifically, I'm going to talk about contrastive learning from the start. So this paper from the lab of Jan LeCun, famous guy on those three names. Well, I think all three of them are pretty famous. The idea they had was to train a network to do feature reduction. So to do the same thing that a PCA or a TSNE would do. So the idea is to train the network so that the output is a feature space that has some kind of semantic meaning and is smaller. Nowadays, we've moved beyond having the feature space being smaller, and we use contrastive learning to just learn good semantic spaces where like images are represented well. Okay, so the biggest bit of this paper is, of course, the equation for the contrastive loss. So just go over each bit of the contrastive loss and we can understand because we are going to implement it later. Okay, so we have as input two samples. Yeah, each one of the x's is a sample. The y is a binary label, and this label is interesting because it doesn't tell us anything about classes. This label is just about whether x1 and x2 are similar. So 0 if the pair is similar, 1 if the pair is dissimilar. If I were designing this loss, I would swap those numbers, but well, I'm not designing the loss, right? W is, of course, the weight of the networks, and it just looks nice when you have the W representing the network. Okay. So D is a distance function, and this distance function can be anything you want it to be, but we are going to use an Euclidean loss, and it's usually an Euclidean loss. And it will define, it will compare the result of the network for those two samples. And now we have two parts for this loss. If the pair is similar, so if y is 0, we'll have a resulting 1 over here. And this bit will be active. And well, if the pair is similar, we want to decrease the distance between both samples. And if the pair is dissimilar, we want to increase the distance between both samples. But because this would quickly lead to an explosion in the space with giant distances, we have a hard limit here. So we're going to increase the distance between both samples until the distance is larger than m, which is a margin. So the margin just limits how much we want those distances to go. Yeah, m is our margin. Okay, cool. How do we implement that, right? So the idea is that we have two networks. They may be the same networks and have all the weights shared. And we have as inputs images that are similar for the first bit. So in this case, they're similar, and we're going to decrease their distance, and it should look like something like this on this fictional multidimensional space. Okay, and then if they're dissimilar, so in this case, they're different classes really, we want those representations to be further apart on our feature space, and only up until we reach the margin. After the margin, it's not that we don't want them to be further away, it's just that the loss will stop working, will become 0 because of this max here. Okay, that was the contrastive loss. And more recently, we had the introduction of the triplet loss, which, as you expect, takes triples as input. So this was introduced by the FaceNet paper, where they designed this for facial recognition. So they want to have a space where one face is closer to another picture of that same face, and it's distant from a picture that it's not from the same face. Okay, so this is our triplet equation. I think this equation is simpler and more elegant than the other one because it just packages everything together and we don't need the label anymore. So we have as input oh, I didn't highlight the anchor. Okay, so XA is our anchor. So this is just our random sample. XP will be our positive sample, which means it's similar to the anchor. And XN will be our negative sample, which is dissimilar to the anchor. And then we also have a margin, but the margin now, it limits the relative distance between the distances between the anchor and positive and anchor and negative. You can see it's still positive for the positive distance, which means this value will go down, and it's negative for the negative distance, so this value should go up. But they only go up and down as long as the difference between those distances is less than the margin. And this creates a scenario where you see the margin that I drew here. It's not a circle margin. It's more like an arc. I don't know how to say that shape. Yeah. So the idea is that in contrastive loss, one of the failure cases when you have thousands of classes, like is the case for facial recognition, what would happen is that the network would learn to represent one class as a single vector. You would try to make every sample from that class or every face from that same person to be the same vector. And we don't want that. That's not very healthy for a semantic space. We want those to be close, but not the same. So that's what using the triplet loss would avoid. Okay, yes. Notice how the margin is between the distances, and this avoids the issue of representing similar objects with the same vector. I just have to say that even though triplet loss creates better spaces, it is also less stable to train, and that's because it has a saddle point. I had forgotten what was the name. So it has a saddle point on the loss definition space, which means that if your network for some reason gets to a point where it's trying to generate very similar vectors for everyone, the distances here will be very close to zero. The distance of distances will be very close to zero, and that is very close to a saddle point. And then the gradient will, vanish, and then you don't learn anything. So if you're trying to learn with triplet loss, be aware that is very likely to happen unless you do some kind of regularization. So regularization can be doing curriculum learning and starting with contrastive loss and then introducing triplet loss. And it can also be just training for classification as well as training for triplet loss. That is enough to keep it in check and avoid falling into the saddle point and being lost there forever. Okay. And oh, I got very quickly to coding time this time. Okay, so I'll ask the organization to change the screen that I'm sharing. Just let me share my browser. Browser. Hello, browser. Okay, thank you. So this first bit, you can remove because it's only for us because we share devices, and I need to tell my code that we only want to use one of the GPUs and not the whole server. Let me refresh the page because it has a little bug with rendering when you leave it open for a while. Okay, now it's back. So we're going to use MNIST because it trains really quickly and we don't have a lot of time. So I'm just showing that the range of MNIST needs to be fixed here. So we're going to divide everyone by 255. And we're going to add an extra dimension so that we can use convolutional layers. Yeah. Now, this is the bit where everyone gets stuck when designing for contrastive or triplet losses, and that is that the loss does not take as input a target and an input. A target and a predicted target. What we need to have is a pair, and this pair needs to have a label telling us whether it should be a similar pair or it should be a dissimilar pair. So the first step is that you have to decide what it means to be a similar pair or a dissimilar one. And we'll decide right now that for MNIST, a similar pair is a pair that has the same class and a dissimilar one has a different class. And okay, that's good. We have some rules. And now we still need to make a data set. So what I'll do is that I'll create a class index so that we can retrieve samples from a specific class at any time. And I'll also create a negative samples index, which is like, if you have a sample from class 0, I want to take a negative sample that is not from class 0. So I'll just make a list that has all the classes that are not myself. It's all very simple stuff just to help us. Okay. So for our first index, it's going to be really simple. We're just going to go over, well, I'm going to zip those. Let's zip those two. Too many parentheses, but doesn't matter. Okay, so we want to have a class index going to be empty. And well, actually, I wanted to have one list, one empty list for each class. I know it has 10 classes, right? And then we are going to take, so this will be an XY. I'm going to append each sample to its designated list that represents this entire class. Okay, that seems good. And now we're going to have what I call the negative index. And it will also be a list of lists, one for each class. But this one is much simpler. So I'm just going to go over the classes. So just arrange to 10. And then negative index at Y will be, well, everyone at first. And then we remove the class itself, right? I hope you can see where we're going with this. Remove I, okay. And now we need to build an iterator using those two indexes that we've just made. I think it's made. Okay, so let's make an iterator. Yeah, contrastive generator, iterator, however you want to call it. And the first step, we're going to go with while true, because this is a Python generator. I don't want it to ever stop. I'm going to import random, because I want to take random samples. And I'm going to take the index, a random index. So that would be random. I think I can do random choice directly on the train set. That will work. Yeah, but that's not good, because then we don't have the index of the class, right? So just a random int into, well, from 0 to the length of the training set. -1, because I think the range int is inclusive. And now we have our XA. So our XA will be xtrain at IDX. And we have our Y, which will be ytrain at IDX. And now what I'm going to do is I'm going to first get a positive pair and then get a negative pair, right? So first a positive pair. So a positive pair will be simply taking a random choice from the class index. Yeah, random dot choice. And we're going to get the class index at Y. This should just give us a positive sample. And then we can use our anchor, our positive sample, and our label. Our label 1 means it's, oops, sorry. 0 means it's a similar pair. And now I'm going to choose a random negative class. So same idea. Negative index for y. And do this and take a negative from this negative, random negative class. And we're going to use another pair. So the anchor, the negative, and label 1. Okay, so how do I use this to train? Well, to make it really quick, well, we want to do a TensorFlow dataset. So I'm just going to do a contrastive dataset here. Will be a TF dataset from generator. And we're going to give it our generator. And we also need to specify how this output will look like. So I'm going to cheat here because I never remember what's the syntax to do this. But basically, you're going to list all the shapes that are going to be used. Yeah. So all the shapes. Can you look better, please? Okay. So you can see we're just listing that the output signature is going to be one image, another image, and a label. So I'll just run these. Oh, okay. We did something wrong. Not enough values to unpack where for x, y, z. Oh, okay. So maybe this parenthesis does do something. Sorry. Our contrastive generator, and did that work? No, it did not. So what is wrong with this one? Oh, we're missing one parenthesis. Okay, now we have a contrastive data set, and I'm going to also do a test data set, which will be quite simple. It will be just taking the data set as is, as we would usually do for anything else. So TF dataset from tensor slices. So we want to do X test, and we also want to do Y test. And then I'm just going to break a line, place those two into parentheses. We'll actually need 2 of those parentheses, and then TF data zip, I think. I hope this works. Okay, it doesn't. I guess it's dataset.zip. Okay, we're good. So the test dataset is just the normal way to prepare it. Okay, so we're going to make a very simple network, 2 layers, max pooling, global average pooling, all the things. Our last dense layer here, it has size 16. I just did this to make it faster to train. But here, this number is how large in dimensionality you want your feature space to be. So if it's larger, it will probably take a little while longer to train, but you may have more semantic features embedded in it, or you may also have an overfit space to the training data. Just try to tune that value to what you need and what kind of accuracy. And also, the bigger the feature space, the harder it is to do search. So if you're doing search, just take this into account. Okay, we have a model, very few parameters. We have an optimizer. And now, the moment everyone's been waiting for, we are going to implement the contrastive loss. Okay, so what we want for the contrastive loss first is to define our distance function. And I'm going to use Euclidean distance. So just the usual stuff, A, B, and we want to, D is going to be A minus B squared, right? And then we return the square root of D. except that if I do this, a mathematician somewhere will probably die. A discrete mathematician, probably. So I'm just going to save this from explosion, because of course, if this number doesn't have a square root, it's going to explode. If anything goes wrong, if it's too close to 0, it's going to explode. So just, if it's not, if it's below 0, just make it very close to 0. Yeah, let me just do that. Yeah, okay. That's Euclidean distance, and now finally our contrastive loss. Now, well, we're going to have as inputs our A, our B, and our S. I'm going to call it S for similarity. Sounds good. Maybe I should follow this, just call it Y. Okay, Y. Y is fine. So we're going to get the distance between the two. A, B. And what we want to do is get, okay. So the positive bit is just, we don't do anything, it's just the distance. And the negative is, we are going to do the maximum with the margin. And I'm going to decide right now that the margin is going to be 1. Why? Because 1 is a good number. People like to start with 1. And if it doesn't work, you try something else. So 1 minus the distance. Okay, and now we just return basically the form, the equation. So 0.5, 1 minus y times the distance plus 0.5 times y times the nth distance, the negative distance. And because this is all happening on batches, I'm going to take the mean, because otherwise it will return a vector for each of the samples. Okay, and now we can finally train. So I did the whole loop here in the train model trainer and loop, but I left the actual computation for the gradients here for us to do together. So, okay, what do we need to do? We need to get features for A and get features for B, and then we need to get those into the loss function. So we're going to apply our model. It's called encoder model twice. So we're first going to apply the encoder model to A. I'll call this A representation. And we're going to do it to B. I'm going to call this the B representation. So the S. There's an S here because this is a batch, right? And then we can compute our loss. We have everything we need. Contrastive loss will be A rep, B rep, and all the Y's. And this should probably work. Well, at least if I run the things. Okay, this looks good. This also looks good, but of course doesn't tell us anything because it didn't run any of those functions. And now we can train. As I told you, it doesn't look that good. The name of the dataset is wrong because Leo from the past gave it. The name is inverted. Okay. Okay. And something else is wrong. Oh, okay. Generator yielded an element of shape 28111. Oh, I know what happens. I think I ran this twice. And now our data set has too many dimensions. Okay, now not working. Okay, generated yielded elements of shape 60,000. Okay, did something wrong again. Probably on the generator, yeah? Or on the index. Okay, yeah, that makes sense. So we don't want to add the entirety of X train here. Just X is fine. Okay, one more time. Well, actually, I'll just keep fixing those bugs until it works. Module TensorFlow does not have an attribute squared, doesn't it? How do you? Oh, I think it's not squared, it's just square. Okay, one more. Input Y, yes, I know this one. I've seen you before. It's complaining that Y here is not a float. It doesn't like when things are not of the same type. I'm just going to cast Y to be TF float. Okay. Why? Again? Oh, it's because we used maximum D square. I did cast you. It's wrong now. Okay, I'll just run and actually pay attention to the error this time. So this is in 1 minus distance. Oh, okay. The 0 is not a float. TensorFlow is going to kill me. That is better. That's a new error. Dimensions must be equal, but are 32 and 16 for one of the operations. Okay, why? Why would it be? Why would it be 32 on the which multiplication? 32. If anyone has an opinion, because I did code this before, and I did not see this specific error before. So the problem is someone is 32 and someone is 16, but why? I'm just thinking. I don't know. Maybe I'll just cheat. What is the difference between you? Well, it's the same thing. You trust me, right? Okay, we're just going to take this from here. The emergency code. Yeah, just leave the quit in there. Yeah. This should definitely work unless the problem was something else. So, okay, the problem was something else. This is not defined. Yeah, I called it differently. Sorry. Distance. And I was missing a square. I don't think the square was the reason this wasn't working. Name margin is not defined. Yeah, of course it's not. So I did it differently before. Okay. We'll get there. We still have 7 minutes to do this and the triplet. Isn't that fun? Yes, you're supposed to be Y. And you're also Y. .5 a type approach instead. Okay, we're running out of time. So we did try, but we're going to move to the code that works now, if that's fine for everyone. Just so we can cover the triplet as well. But you can see the struggle of coding, especially if it's live. And this one actually works. I still don't know what the difference is, but okay. So it will train for a bit. I told it to train for 10,000 steps. So while it trains, I can go over the remaining code. Yeah, so evaluation is simple. We just run the network through all of the test sets, and well, that's it. I'm just saving the categories here so that we can plot later. But really, you don't need to. You don't even need to have labels if you know what similar and dissimilar mean for your application. Here we're going to do PCA visualization. So we're almost done here. So just wait so that we can see the visualization live. Okay. So it is expected that this looks very nice and the colors look well distributed, and they do. I know it doesn't sound that good, but there are a lot of samples here. I think there are 10,000 samples, so you can see how the clusters form. And also, this is a PCA and not a TSNE, so the clusters will look ugly anyway, because it's just compressing those 32 dimensions in a procedural and not a learnable way. And most interestingly, is that now we can do search with those numbers. So the search function is super simple. We just get the vector representing each image, and then we compare them with Euclidean distance. And then we sort, and we get a search application. So you can see it's not perfect, but it's very, very good, because even though this is not innate, it has a very similar shape. So our representation is creating a very nice semantic space. Okay. And well, our triplet loss, what we need to change from the contrastive loss is not much. So the dataset arrangement is different because we need triples and we don't have a label anymore. We need a new network and the loss function, basically. Okay, so the difference here is that we're using the same indices, right? We're using the same things we were before, but now instead of using a positive and a negative and a positive and a negative, we are going to use an anchor, a positive and a negative all together. Yeah. We create the data set and we remake the model. This is the same model. I'm just doing it again because I did look, there is no easy way to reinitialize a model. It's always very complicated. So just remaking it. And finally, the triplet loss. Now, you can see that the triplet loss is less fidgety to implement than the contrastive one. Just do Euclidean distance and basically copy the equation, and it works. It's great. It's fine. Right, we have our reduce mean. You notice that on the code that is on GitHub, I did make those losses more flexible because you have a loss maker where you can say the margin that you want to have. So we use our loss maker to make a new triplet or a new contrastive loss with different margins. So this is a different margin. We're using 0.5 here. And on the training, on the model trainer, what we have to do is get each of the 3 representations. So you're going to run the model 3 times. And of course, I'll just give the example. I work with cross-domain data. So I work training representations for sketches and images. And in our application, a single model can usually handle sketches and images. So we would have 2 different models, but everything else would be the same as you're seeing here. And we compute, we apply the gradients, we run the training. I think I forgot to make the triplet loss. Okay, it's going to train. And this is interesting. So when all of the times that I ran this before this presentation, the triplet loss didn't work. So if I keep training, they will all go to a similar space. And if you look at the loss, you can see exactly why. I mentioned during the presentation that the triplet loss has this saddle point that is very close to when all the representations look the same. And this is exactly what happens, because if all of them look the same, what you have as a result of this equation is that you have the margin, because those 2 cancel out because they're similar, and you have the margin. And when this happens, your training is not going to work. And then you just need to add some kind of regularization, as I mentioned, like just adding a cross entropy loss together with the triplet would very easily stabilize this and make it look much better. It will probably look terrible, and the search will probably not be very good as well. Well, that's better than last time. Yeah, still not great for search. Maybe there's a single class that works for this, and not very well for the others. And that is all. Thank you very much. And I hope I was able to explain a lot of stuff. Yeah, I see questions. Oh, someone tried to help me. Okay, thank you, GDA 1988. And Moacir asked if it would help to have pre-trained weights before training a triplet or contrastive loss. And yes, it would help a lot. That is one of the ways you could do regularization of the triplets and also the contrastive. So one of the works we did in the past involved doing curriculum learning, where we had three stages. The first one was just pre-training a network with classification. Then we applied contrastive loss with classification, and then we applied the triplet loss also with the classification, and that created a great search space for sketch-based image retrieval. Okay, Juranji, yeah?
No, we have another one. You can read,
okay.
Yeah? No,
okay,
you can answer that, yeah.
Okay.
Do you want to read?
Instead of, yeah? Instead of distance measures, what if you're using ranking measures? Relative positions are more relevant than absolute distance values to compare whether 2 images are similar or not. Okay, in this case, you would have to come up with derivable, how do you say that word? When a function can be, has a derivative, yeah, has a gradient. You have to define your ranking using a function that you can take a gradient from, so that we can have learning working in some way. Yeah, I'm not aware of any of those, but I've seen papers that do exactly this. So if you search for it, you're going to find some. Okay, that was the last question.
Very nice, Leo.
Thank you.
I love the step-by-step of coding and show that, oh, it's not working. No, let's try that. Oh, no, it's not working again. Let's try to do another thing. No, that's real life. So very nice. We have a break now, and we'll be back in 15 minutes, okay? So thank you so much, and see you. soon.
Okay.
Bye.
See you. Bye. Thank you.
Thank you.
Vincent, acho que o microfone está desligado.
Oh, thank you. So I will repeat everything. I thought that we are back, and we have 4 parts for the last part of this tutorial. And Gabriel will talk about self-supervised learning. Fernando will talk about task augmentation, Moacir activation functions plus evaluation, and everybody will close the session, the tutorial sessions. So Gabriel, now it's up to you. Thank you.
Thank you. Well, as part of the tutorial, we're going to talk a little bit self-supervised learning. But first, we need a little bit of context here. So we know that given a task and enough labels, we know that supervised learning can probably solve it really well. But we also know that large amounts of manually labeled data can be very costly, time-consuming, complex, and expensive to obtain. And sometimes in real applications, they require categories that are not present in standard large-scale benchmark datasets, for example, for medical images. And in some cases, we do have vast amounts of unlabeled images. So the idea here is that self-supervision is a form of unsupervised learning where the data itself provides the supervision. But, well, this idea here has been widely used in language modeling. For example, an usual task for a language model is to predict the next word given the past sentence. So self-supervised learning relies on pretext tasks that can be formulated using only unsupervised data. So by producing those surrogate labels, those tasks can make use of those generated labels to guide the learning process. So in fact, here we're interested in the learned intermediate representation, and we hope that this representation carries good semantic or structural meaning. So the pretext task here guides us to a supervised loss. However, we don't care about the final performance of this task specifically. So you can think that those models, they predict part of the data from other incomplete, transformed, distorted, or corrupted parts. And you'll see later, most models, they learn to compare using some kind of contrastive learning strategy. So nowadays, those models, they are able to learn useful future image representation in order to solve those tasks. And they actually achieve state-of-the-art performance when we consider methods that rely only on unlabeled data, so benefiting almost all types of downstream tasks. So in this presentation here, I will give a general overview of the methods, but be aware that the implementation details can be very important for each method. So at least I'll show an overview of the most cited articles that use the term self-supervised learning, specifically for the vision. So we encourage you to read the full papers of the determined tasks which are going to re-implement it. So most works do use the basic structure of CNNs, but very often they modify, for example, the training losses, the architectures, and the batch manipulation, and some methods, they require a lot of GPU power, and some of them, they need distributed training across multiple GPUs. So we start with one of the early works, at least that use this term, self-supervision. Well, in this work here, called the exemplar convolutional neural network, we are going to train a network to discriminate between a set of surrogate classes. So we are going to first sample n patches from different images at various positions and scales. And ideally, we are going to sample those patches from regions containing considerable gradients, as though those areas cover edges and tend to contain objects, or parts of objects. So they are the exemplary patches. And we are interested in patches containing parts or objects. So then, now that you have n patches from different images, we're going to apply a variety of random transformations to each patch. For example, can be translation, rotation, scaling, and other transformations. And then, all the resulting started patches are going to be considered to belong to the same class. So intuitively, this problem described here serves as to make sure that the different input samples can be distinguished. At the same time, it enforces invariance to the specified transformations. So the pretext task here is to discriminate between a set of surrogate classes. So you can see here in this image, we have a lot of patches. So if you select this deer patch, for example, we're going to apply a variety of random transformations. So after we've done that, we are going to consider all of those new generated images as the same class. And then you just do it for multiple patches, obtaining that way multiple classes. So there are some things to consider here. For example, we can arbitrarily create as many surrogate classes as we want. So it is important to consider the number of surrogate classes, the number of samples per surrogate class, the types of transformations that we are going to apply, and you have to notice that in this task, the resulting feature representation is not class-specific. It provides robustness to the transformations that have been applied during training. So in this next work, where they called context prediction, the task here is to train a network that predicts relative location of two randomly sampled non-overlapping image patches. So here the model needs to understand the spatial context of objects in order to tell the relative position between parts. So the first thing we are going to do in this task is to randomly sample the first patch without any reference to the image content. And then, considering that the first patch is placed in the middle of a 3x3 grid, the second patch is going to be sampled from its 8 neighboring locations around it. And we have to predict which of the 8 neighboring locations the second patch is selected from. So it turns in a classification over 8 classes. So as you can see here, considering the middle patch, in this case the nose of the cat, we are going to sample a second patch. And it can be this patch number 1, 2, 3, 2, 8. So in this example, if you sample the patch of the right ear of the cat, our target solution is the prediction of the location 3. So things here to consider. To avoid the model catching low-level trivial signals, they add gaps between the patches and some small jitters, and they randomly downsample and upsample some patches, and they use some other additional noises. So in this work here, where they called it jigsaw, here they train a network to place 9 shuffled patches back to their original locations. So the first thing we are going to do here is to define a set of jigsaw puzzle permutations and assign an index to each entry. And then we are going to randomly pick one such permutation and rearrange the 9 input patches according to that permutation. And then we are going to ask the network to return a vector with the probability value for each index. So, given an image here, we apply a random permutation, and the network must rearrange those patches. So, in this case, a convolutional neural network processes each patch independently with shared weights and outputs a probability vector per patch index out of a predefined set of permutations. So, this is another task called colorization, and here the model is trained to color a grayscale input image. So precisely the task here is to map an image to a distribution over quantized color value outputs, and the model outputs colors in the LAB color space. So, given the channel L that represents perceptual lightness, the model must output the channels A and B that represents red and green, blue and yellow. So here, given an input in lightness, we have to map these colors to the AB channel. There are some observations here for this task, that the distribution of AB values in natural images is strongly biased towards low AB values. So this causes a class imbalance problem, and that's why it is necessary to use this quantize method. And there's another work here, context encoders. The authors, they propose an inpainting task, where the model is trained to generate a missing region that was arbitrarily removed from the image. So the model here is trained with a combination of a standard pixel-wise reconstruction loss and adversarial loss. You can see here in the image that given a missing region, the task is to generate it. The authors found it important to connect the encoder to the decoder through a channel-wise fully connected layer, which allows each unit to the decoder to reason about the entire image content. And there is another task here called split brain. The authors, they use an autoencoder with a split in the architecture. So this will give us two separate subnetworks. And each subnetwork is trained to predict a subset of the channels of an image in relation to the other channels. So you can see here in this image, instead of using a traditional autoencoder, two subnetworks are trained to do complementary predictions. So one network F1 predicts X2 from X1, and the other network F2 predicts X1 from X2. And this is a cross-channel prediction task. So the proposed task here changes the problem from reconstruction to prediction. So you can see another example here, that in this image, given an input image X, it is separated into a grayscale channel X1 and a AB color channels X2. Then F1 predicts the color channels given the grayscale channel, and the F2 predicts the grayscale channel given the A and B color channels. In this task here, the authors, they explored the task of segmentation using motion on videos. So in some works, they explored the self-supervised task using videos. So, but for this presentation, I just show this one. So the first thing you have to do is obtain the supervisory signal by segmenting an image into foreground and background, considering the optical flow between the neighboring frames of a video. And then we're going to train a model to predict this segmentation from a single image. So the key idea behind this work here, behind motion segmentation, is that if there is a single object moving with respect to the background through the entire video, then pixels on the object will move differently from pixels on the background. So it is possible to use the unsupervised motion-based segmentation as a ground truth to train a network to segment objects from a single frame. So in this work here, multitask self-supervised visual learning, the authors here, they combine multiple tasks, and they show that it always improves performance. In this case, they use those tasks that some tasks that I presented earlier, like the relative position, colorization, the exemplar task, and motion segmentation. And you can see here that the feature obtained from the combined tasks was better in this case. So it shows us that sometimes we can combine some tasks and the feature will be better. But it's not so simple because the input channels can conflict. For example, when jointly training, for example, the colorization task and the exemplar task. the colorization receives grayscale image as input, while the exemplar task receives all the color channels. So the second sort of conflict that we can have when mixing tasks is that one task learns, for example, semantic categorization, for example, generalizing across instances of a class, and the other learns instance matching, for example, which should not generalize within a class. So all of this may be taken into account. In this article here, specifically, they propose some kind of input harmonization for the first problem, and for the second problem, they use a combination of features from different layers. In this work here, called rotation or RotNet, the task here is to predict image rotations. So here we are going to simply rotate the image into 4 angles, and then the model is trained to predict which rotation was applied. So it is a 4-class classification problem. So as you can see here in the image, if no rotation is applied, then the label is 0. If 90 degrees is applied, then the label is 1. If 180 degrees, the label is 2. For 270 degrees, the label is 3. You just train the network like a normal CNN. And here, in this other task called AET, the authors they perform transformations on the input images through some operators, and they train the autoencoders that are able to directly estimate those operators. So the idea here is that given a randomly sampled transformation, the model seeks to predict it. So here is an image. The transformation T was applied to the image X. So the loss quantifies the difference between a transformation T on the left and its estimate T hat on the right. And their goal is to learn an encoder that aims to extract the representation E of X for a sample X. And while they do that, they wish to learn a decoder, which gives an estimate T hat of input transformation. So since here the prediction on the input transformation is made through the encoder features, then the original and transformed image, it enforces the model to extract expressive features as a proxy to represent images. So in this work here, called PER, the objective here is to approximate the representation of the original image with its transformations, its contrastive loss. So in here, the authors they use a memory bank of negative samples to compute the loss. So here you can see that instead of predicting properties of the image transformation, this task constructs image representations that are similar to the representation of transformed versions of the same image and different from the representations of other images. So here they adopt the jigsaw pretext tasks in a way that it encourages the image representations to be invariant to the image perturbation. So in this case here, the negative samples are obtained by computing features from other images with a memory bank. And this memory bank, you can see here in this image, is an exponential moving average of feature representations that were computed in prior epochs. So this allows to replace negative samples by their memory bank representation without having to increase the training batch size. In this work here, MoCo, the authors they view the problem of contrastive learning as a dictionary lookup problem. So, given an input image X, the intuition here is to learn a representation Q by a query encoder here on the left that can distinguish X from any other image for a set of other image X keys. So while this encoder is updated by backpropagation, the momentum encoder is updated by linear interpolation of the two encoders. So the momentum encoder is on the right. So you have the momentum encoder as a moving average of the original encoder. So just to show here. So instead of using an end-to-end or memory bank approach, this method here, the MOCO, you can see in the image C that a query is matched to a key in a dictionary. So, and then to have a large dictionary, they maintain the features in the previous batch as a queue, and the dictionary consists of the current and previous batches, and is not limited to batch size. So, to improve the consistency of the features, this momentum encoder is slowly updated, and this allows for high performance training without large mini batches. In this work, called BYOL, they use a fixed randomly initialized network to serve as the key encoder. So you can see here that given an image X, we're going to create two augmented views, and they're going to be encoded into representations and projected into latent variables. Actually, though this projection here is just MLP. And then the online network in blue outputs a prediction. Note that only the online network, this one in blue, has this predictor queue. And then it just uses the L2 error between the normalized prediction and the target. So these online and target networks, they interact and learn from each other. So they train the online network to predict the target network representation of the same image under a different augmented view. So at the same time, they update the target network in red with a slow moving average of the online network. So here's just the L2 loss they use to compare the predictor and the target. So the authors point out in this work that it does not collapse probably because of the addition of a predictor to the online network, and because they use a slow moving average of the online parameters as the target network. So in this other work here, SIMCLR, we have an encoder F, a projection G, and H is our representation. So here in this work, they do not sample negative samples explicitly. So they use the contrastive loss to maximize the similarity of the two projections from the same input while minimizing the similarity to projections to other images within the same mini batch. So they maximize agreement between different augmented views of the same sample via a contrastive loss in the latent space. So here what they do is that they randomly sample a mini batch of n examples, and this is going to give us a total of 2 n data points that are the augmented examples derived from the mini batch. And then just given a positive char, they just treat the other augmented examples within a mini batch as negative examples. So a note here that this model, because of the way they compute it, it needs a large batch size to incorporate enough negative samples to achieve good performance. So I think the standard they use 4096 as batch size. It's really huge. In this work here, called SWAV, they propose a swapped prediction contrastive objective to deal with multi-view augmentation. So the traditional contrastive instance learning idea that we already saw in the previous slide is that we take the image and then form two augmented views of the same image, and then we compare their features. But here in this work, the difference here is that now that they have the features Z1 and Z2, they do not just compare these features with each other. They map these features to the nearest neighbor in a set of clusters. And this is a finite length cluster codebook, and they use it to look up the codes that are most similar to the features. So now the idea is that from this code Q1, you should be able to predict the feature Z2 of this image. And how they map the features to this codebook is a little bit tricky, but the general idea is like given an image, you obtain their features with a network, then you're going to be mapped to prototype vectors, assigned to a cluster, and then we're going to swap this assignment and give us a target to predict. Let's show it again. So the big idea for this work, behind this work, is that, for example, typical clustering-based methods are offline. So in the sense that they alternate between a cluster assignment step, where the image features of the entire dataset are clustered, and a training step, where the cluster assignments are predicted for different image views. So they require multiple passes over the dataset to compute the image features necessary for clustering. So, but here they compute the codes online, allowing this method to scale to potentially unlimited amounts of data. So here in this another work here called SimScience, we are going to create two augmented views of one image that is going to processed by the same encoder network F. And then a prediction MLP is applied on one side and a stop gradient operation is applied to the other side. And then the model maximizes the similarity between both sides. So the loss here is this loss D here is the negative cosine similarity. So we're going to, given an image X1, we're going to have those features Z1, then we're going to a predictor H, we're going to obtain the P1. Then we're just going to compare this P1 with the feature Z2 on the right. And the loss is actually symmetrical, so you're going to do this for the both sides. The thing here is that the stop gradient operation here that is applied on the one side is enough for this model to not collapse. So we saw on those presentations that we can learn features in multiple ways. So for example, let's compare, for example, the SimCLR. They compare the similarity and the dissimilarity of samples. In BioL, they use a moving average encoder, momentum encoder. And in SWAV, they use this algorithm here, the SimHardNop, to cluster the data online. And in this work here, the SimScience, they just use a stop gradient operation. So you can think that this specific work here simplifies things and can be viewed like SimCLR without the negative pairs. You can view like BLL without the momentum encoder and SWAV without the online clustering. So in this next work here that I'm going to present called Barlow Twins, you can see that the basic idea is almost the same from those last works that I presented, like given an image X, then we're going to apply transformation to this image, obtain two distorted images, and then we're going to extract some features, Z1, ZA, and ZB, and just going to compute the cross-correlation matrix between the embeddings of this network. And then we're just going to try to make this matrix close to the identity. So this loss has two terms, one inverse term and one redundancy reduction term. So the first term here, by trying to equate the diagonal elements of the cross-correlation matrix to 1, it makes the embedding invariant to the distortions applied. And the second term, the reduction term, by trying to equate the off-diagonal elements of the cross-correlation matrix to 0, it decorrelates the different vector components of the embedding. And this decorrelation reduces the redundancy between the output units, so that the output units contain no redundant information about the sample. So I just gave you a generalized summary of the methods. If you want to learn more, there are those two articles, Self-Supervised Visual Feature Learning with Deep Neural Networks, a survey, and this other work here, Self-Supervised Learning, Generative or Contrastive. Those are good articles if you want to explore more those self-supervised learning tasks. And there's also this GitHub page where they're always up to date with the recent work. So now let's show you a toy example with the rotation prediction task on the Fashion dataset. Let's just change here. So here in this notebook, you can see that we're going to train the self-supervised learning with the rotation prediction task. So we're going to use the Fashion dataset, just define our batch size and number of epochs. Here we're just loading the dataset, Fashion. We're going to normalize the data. You can see here the size of the training set and our testing set. And before training the model, we are going to define a generator that will give us the rotated image and their labels. So given a training data and a batch size, we're going to loop here for the generated. We are going to get the number of samples. That's the number of the training data. And then we are going to start from the index 0 to the number of batch sizes. Then the next loop here will be the batch size through 2 times the batch size, and so on. So inside this for loop here, we are going to get the samples you use in this batch. And then we're going to initialize X batch and Y batch. And for each batch sample in this batch of samples, we're going to apply a rotation to the image. 0 is equal to 0 degrees, 1 to 90 degrees, 2 to 180 degrees, and 270 for the label 3. So, but here we're going to generate the 4 rotations for the image, for the same image, instead of each time randomly sample a single rotation transformation. Because in the article, the authors, they say that it is better. So for this image here we're getting from the batch samples, we're just appending them to this list. That is our X batch. And then because we did not apply any rotation, the label it's going to be 0. And then for the same image, we're going to rotate it 90 degrees and the label is going to be 1. For the same image here, another rotation 180, the label is 2. Rotate 3 times 270 degrees, and then here the label is 3. So note that the actual batch size here will be batch size multiplied by 4, like the original article, because here we're generating 4 rotations for the same image in this loop. So here we just make sure there are numpy arrays, and this is going to give us the next batch of training. just initialize the generated here, and we can visualize some rotated images. You can see for every image we have the original image and the 3 rotations applied. You can see here that they are in sequence. And then here we're going to build our model. So fashion emnist size is 28 by 1008. And then we're just going to use some basic model here like some convolution, so max pooling, convolution again, global average pooling, this dense layer with size 60, and we're going to use this feature as representation. So just keep in mind this layer here. And then the last layer, a softmax layer, has far, because as we noted, the rotation task can be viewed as a far class classification problem. So here is our model. The last layer has far, size of 4, softmax. Just going to compile our model here using basic Adam optimizer and use the categorical cross entropy. So here we're going to pass to model.fit our train generator for this number of epochs, and we're going to train it. And after 100 epochs, you can see that the training loss is close to 0 here, and it takes a long time. So let's visualize the features that we learned, and for that we're going to use 2000 images from the test set for the visualization. We are just getting the X test and Y test for the TSNE. And here our feature model is going to be the 16 dimension layer as the feature extraction. So given the feature model, we're going to predict all the X test images. This will give us a feature array. Now we have here the 16 dimension feature representation for the 2000 images. And this here is just the code for the TSNE plot. And this is the result we get. We can see here, for example, that the sneaker here is close to the sandal, which makes sense. We can here see the ankle boot, so it's near here, the sneaker too. Here we can see another cluster of the trouser, dress. In this middle here we have the shirt. So without explicitly training to recognize classes, we can see that we learned some good features, because our feature representation is just like 16 dimensions. Really, it's not big. So just do some SVM classification. Here we're going to divide the test set in two. The total test set has 10,000 images, so we are going to use half 6,000 images of the test set to train the SVM, and the other 5,000 to test the linear SVM. And you get an accuracy of 70%. So here, let's just do some tests here. Now let's generate the same plot, but of the features, but without training the model. Let's just see like what a randomly initialized model gives us. So here you just have the random model here. It is not going to be trained. Here we're going to plot it, and we can see that no, the features are actually not that good. And we can see that with the rotation task, we could get some good features. That's not a highly specified training method here. And for the SVM, if you do it without the training, we have this accuracy of 26% with the classification score of the model without training. So the rotation prediction task here is, although it's not trained to recognize separate classes, we can see that it learned some good features. And if you have the time here, 1 minute, okay. I'm just going to show you the other task, self-supervision, but it's the barrel twin tasks. So here we're going to load the CFAR10. Oops. Okay. Just let me show the right screen here. Yes, that's the correct. So, okay, the first thing here, we're going to load the CFAR10 dataset. We're just going to, this is the dataset. We're going to train on the Tyra data. And then we're going to define some augmentation functions here. So this function here is just a random resize crop. We're going to randomly crop the image, and then we're going to resize it back to the original image size. This image here, we are doing some random crops. We have this solarize function here that given an image, it outputs given a threshold, same value. And here I'm going to apply some random brightness, contrast, saturation, hue, and we also going to have some color drop. And this function here is to just randomly apply some of those functions that we defined here. So we're going to define the dataset views of our images. So in dataset 1, we're going to get from the X-train, in dataset 2 also, but here we're mapping the dataset through this custom augment function. And just here, later we're going to pass to the training the dataset views here. We're just going to zip the dataset 1 and dataset 2. So we have to make sure that they are aligned here. So let's see if we're getting different views of the same image for every group of images. So for example, this dataset 1, we have a cat here, and here we have also a cat, and it's the same image but with other applied distortions. Okay, then we're going to define the barrel twin loss. It's just calculate this empirical correlation matrix here and do those operations. They are here. Here are our ZA and ZB normalizations. We're going to multiply and get the cross correlation matrix, and those are the other terms of the loss. And here we're going to define a class to train the model. The model is going to have an encoder and lambda here. It's just a regularization parameter. And then we're going to get the two views of the data, view 1 and view 2. We're going to obtain ZA and ZB. If you pass those views through the encoder, you can see here that it shares weights. And then you're just computing the loss and the gradients, and that's it. You're just using a basic model here, but here you're going to use a MobileNet V2. Here you are pre-processing the data inputs here. You have some layers here that it's important for this method to have MLP layers in the final. So you have 3 here. Then just going to call the model and compile the model here and fit. You can see here that the training loss, it's not like this basic classification task. It starts very, very high. And here just extracting some features of the test set. So it's going to be the 512 dimension layer, and we are going to visualize those features that I extracted the features from all the test set. And you can see here we can see some clusters more or less. And I did the same thing here, but without training the network, just to see how the representation space is. So I don't think we can truly say that the model is learning awesome features, but at least it's better than the random network, and it's just a toy example here. So that's it with my presentation. Thank you. I think now Fernando is going to present.
Yes, thank you, Gabriel. I will continue. Let me share my screen. Just a moment. Yes. So we already talked about the data, the training, the structure of this network, how to prepare the data, how to prepare the structure, and different manners of we can train the network. But now we all focus a little bit in the test set. How we can make sure that our train is correct for the test data, right? So I am going to show some notebook here, and we are discuss a little bit about the test augmented. So we can use the data augmentation methodology to increase the training data, but also we can make tests also with augmented test set to make sure that the prediction is right, and our network is robust to different test sets. All right. So I use the CIFAR again. All this code to prepare the network fine tuning, the network training, and the graphics are the same from the CNN fine tuning netbook. But I use the image data generator from the Keras package to generate different data. So we can generate different sets, use different parameters here, receive the test set as argument, and generate different variations of this data to perform the evaluation of our network. So here I have the evaluate for the original test set, and here I have the evaluate for the augmented test set. Note that the difference, it's about 90%. Of course, here we only training for a few epochs, right? So this accuracy is very low for the CIFAR dataset. But we can see that only changing applying a few variations in the test set, it can change the accuracy of our model. So 90% only apply a shift range here of 20%, right? Why this is so important for us? If we apply some variation in the test set, we can see if our model is robust to noise, some different perspective of accusation of the image, and test if we can actually trust in the performance model, right? In addition to the only generate a different test set, we can combine different outputs and study this behavior. So we can apply some average between the two outputs and test the accuracy. We can apply a max value, a mean value, and we can also apply different structures. For example, if we have three more than two test set, we can also apply the most voting output and combine these different results to actually evaluate our prediction model. This idea can also be used not only for fine-tuning and training from scratch. We can also generate a different test set, apply feature extraction using a pre-training model, and combine the feature space and the outputs for an external classifier, and see if the feature it's good for a different test set, right? Because the original set is the same, only a little change in the variation of the pixels from the image is actually changed, right? So it's very important to see if our model is robust to noise injection, mainly because the great issues that Moacir showed us in the morning, for example, different forms of attacks, for example, right? So I finished this test augmentation code alert that we have to not only to be concerned with the network and the training data, but also for the test sets that we are going to use for the validate our model. Moacir is now going to show how we can be sure that our evaluates how we can evaluate our model and to be sure that the results are good enough. All right. We have some question. All right. Moacir.
Hi. Thanks, Fernando. It's up to me to finalizing this tutorial. Let me put this on presentation mode. Okay, let me know if we can. Yeah, I think it's fine. So to end this tutorial, I'm going to talk about alternative activation functions, and then we are going to do final remarks. And after the final remarks, I'm going to call Leo, Fernando, and Gabriel to talk with me and answer questions if there is still time. As you can see during this tutorial, we made this tutorial in an order, a specific order, and this order is the order of importance of what we consider more important when you're trying to train a deep neural network. And what Fernando was just talking about was a way to improve predictions when you have already explored everything around the data itself, the alternatives for training and the architecture as well. And one of the things that people often overlook are the activation functions. So often we have those more common activation functions. I'm just showing you for visualization here, the sigmoid. I remember when I was studying neural networks before deep learning, sigmoid was the most used activation function. It compresses the values into a 0-1 range. And we have also the hyperbolic tangent, which is quite similar to the sigmoid, but it compresses the range of values in between -1 and 1. However, after basically the CNNs started to appear as popular models, the rectified linear unit activation function became much more popular. This is because it is unbounded at the positive side. So this allows the training to happen without limits on the positive side. However, the hello function was also has limitations, and this is why there was for a time people were exploring alternatives for negative values, in particular leaky rectified linear units, which would have a smaller weight on the negative side. The good thing about HELU is that it avoids saturation, because it is not bounded on the positive side. In contrast with the sigmoid function, which saturates, as you can see here, it saturates after a few after some value. And those saturations can cause training to slow down due to near zero gradients. However, there are some negative points. Values of this function that are near zero, they produce non-useful or very bad estimates for the gradient. And numerically, this is a problem, especially due to this inflection point here, which is quite abrupt. So mathematically, this does not behave very well. It may lead to neurons stuck completely on the negative side and always outputs 0. So if we have a specific neuron or a filter that is in the negative side, it outputs 0. And because it outputs 0, it has no gradient. So the network has no way to update this neuron. So it becomes a dead neuron. Leaky ReLU was intended to solve this dead neuron problem, but it still has some numerical issues due to the non-smoothness of the inflection point. Although we do have some strength, some inclination in that line, it has that shoulder that's quite abrupt, and so it doesn't help much. So two other functions were developed, one in 2017, which is Swish. It is a gated version of the sigmoid. In here we have X, which is the input, that is the X is multiplied by the sigmoid function, and the X inside the sigmoid function is weighted by a hyperparameter that you have to define or make it learnable. The function has this shape, so as you can see here on the right hand side, it is similar to a HELU function, but on the left hand side, instead of saturating, it has a smoother transition. Later in 2019, there was this improvement, I would say, in the Swish function that was called Mesh. This function was designed to be unbounded above bounded below is smooth and non-monotonic, and it has guarantees to be so. Instead of using only the sigmoid function, it uses a hyperbolic tangent function within a logistic function. So it is quite similar. If you plot those two values, those two functions, they even look like it seems like there's an error with the slides that I just copy and paste, but it's not. Those are two different functions. However, MISH is a little bit the slope of the function on the positive side is a little bit better to especially for the first terms here. So this is why in practice this function MISH tended to have a little bit more performance than to use a regular hello function. So I'm going to show you a code that shows this in practice. So I'm going to define a class for a MISH activation function layer, and it basically implements this using Keras. It's basically a hyperbolic tangent, and as you can see here, using a soft plus function that is the logistic function that I showed you. And I'm going to modify my residual block code. We have here a residual block that I just made, I just coded from scratch. So basically it's two convolutions that I then add in the end with the input. So I get the input, add with the output of the second convolution, and then I include hello activation afterwards. And I did the same, but using a MISH function instead. To do that, I just include a linear activation of that convolution so that it doesn't have any activation in practice, and then MISH function in at the end. And then I have my residual network here, which I learned for a few epochs. I used a learning rate scheduler here, an exponential one. So in this notebook, I tried to use all the good practices that we have shown before. And then I ran for 15 epochs, and both using hello and using MISH. And in the end, what we observe by using the same seed, so I kind of controlled the initialization and then the batch selection and so on. We observed in training a slightly better value for the loss, a somewhat very important improvement in accuracy, but this is on training. When I go to validation, the loss also drops a little bit, and the accuracy increases by 2% or so. And that somewhat is what you have to expect when using a MISH function. And this is why I didn't put this in the beginning of the presentation of the tutorial, because in the end we are just talking about improving a little bit. Because if you didn't do your basic stuff, it doesn't matter if you're using hello or MISH, right? By looking at the loss functions, they are somewhat similar. So instead of looking into the whole training, I'm just going to focus on the last 7 epochs, half of the epochs. And as you can see here, the green line, which is below, is the training loss for the MISH function, and the red dotted line is the validation loss for MISH. So it tends to be a little bit below when you compare using the hello function, and that can make good impact, but just after you have done everything before we talked about during this tutorial. So to summarize everything that we already talked, and we can discuss those topics in order of importance. If I and this is interesting because we designed this tutorial in a way to give people information that I would like someone to have taught me 5 years ago. So first, you start by looking very carefully at your problem definition and the data you have available. Then you properly formulate the problem. What is the task? What are the possible tasks for the problem I have? And how can I properly evaluate it? And as we have seen it, evaluation is very important, not only internally, but if it's possible, you always wanted to do external evaluation as well. So after you have your problem set, very well defined, the task that you, or the set of tasks that you want to solve, the evaluation, everything is settled, then you design the architecture. Then you must choose which kinds of layers you want to include in your deep neural network. If you are using convolutional layers, recurrence layers, attention layers, and so on. So, and just after designing the architecture, you can then design the optimization procedure. Make sure you use a good optimizer. For example, Adam tend to be a little bit better than regular SGD, but then you make sure that you are going to use a smaller value, not a larger learning rate value. If possible, always opt for a learning rate scheduler so that the learning rate drops over time, or it does not only drops but changes over time. For example, using cosine annealing or an exponential function. And use training strategies to improve. So if you're not sufficiently satisfied with the results after you did the 4 steps that I just mentioned, do not go back to the architecture and try to make it larger. Instead, define strategies that may help you. First, consider using no training at all. If you are using a very small data set, maybe just feature extraction will be sufficient. Always try to use pre-trained weights and transfer learning. So this is a no-brainer in deep networks. If you can use transfer learning, if you can use some previous data set, larger data set, do use it and learn it. If it's not possible, then you may use an alternative task. Consider using contrastive learning for your task as a part of the task, and self-supervised learning as well. As Gabriel showed you, he could achieve 70% accuracy on the features learned by self-supervision and not using classes at all during the training. And this was quite similar to what Leo obtained earlier on by using the classification itself. And then after you went through all this, then you try to improve predictions and performance. And then this could mean augmentation in testing data, that's an option Fernando showed you, and also alternative activation functions. And then after this, maybe you could also try other things, such as go to more recent architectures, more recent papers, and look for ideas that could improve even further your current model. But our recommendation is don't start from the top, start from the bottom and build your model carefully. And as final remarks, deep neural networks have high generalization capability in terms of the representations they learn. Maybe not the generalization in terms of classification or regression or the final task may be debatable, but the representations are often very good, so make use of that. Because of this, significant transfer learning can be achieved, and you must always use if you have the opportunity. Do not forget basic data science and machine learning concepts. They always have to be observed to guarantee that you have better learning. Focus your efforts on improving representations rather than following only the objective functions. And it can be very useful to have not only different tasks that in your toolbox, but also visualizing the feature spaces that you are learning. And then carefully designing optimization and correctly evaluate the model. This is fundamental in this scenario. Do not forget, I cannot stress this enough, do not forget to use the test data only to evaluate at the final moment. Test data is sacred, so you have to always define everything within your training data using validation sets. So I hope you have enjoyed this day with us. Please take a look at our paper that is available on archive. We did put some preprint, but you can also find you also going to find it later on also on IEEE in the proceedings of SIBGRAPI. We also have a previous tutorial. It was 4 years ago, also at SIBGRAPI, which has more basic stuff. So we were learning back then in 2017 about GANs and autoencoders, variational autoencoders, style transfer, contrastive learning, etc. So in this tutorial we have this type of material, and interestingly now we go back to even more basic stuff, but then now much more experience. So thank you, and I guess we can call back our other participants.
Oh, very nice. You all did an amazing job, because it's a lot of stuff to cover in this tutorial. So thank you so much. I think it will be very helpful. So we have some questions here, but I'd like to make one. And what should I know before learning deep neural networks?
That's a good question. Before trying to learn even the subject, you mean?
Yeah.
I think before trying to, well, the others can complement after, but I think before trying to go directly to deep learning, it is very important to get in touch or be exposed to the basics of machine learning and data science in general. So learn how to what are the common issues in data, and then learn how machine learning operates in terms of the various paradigms it has. So it's not only supervised learning, but we have we talked about self-supervision here, but there's also unsupervised learning, and how does it work in a more shallow environment. And then when you know that you have I won't say master, but at least be exposed to this basic stuff, then you can go and look into deep learning. And mostly because if we talk with people, for example, in the industry and in practice, they don't use deep learning that much as we think, because we always have to come up, if you can use a simpler solution, you should always use the simple solution if it works. So in practice, this is much more important than go directly for deep networks. Yeah.
Anyone would like to add some comments? No, no.
Sorry.
Okay.
That's fine.
Are you take the opportunity that we have here a professor, a postdoc, a PhD student, and a master student here?
Yeah.
And I would like to know what advice can you give to someone who has started learning deep neural networks? I know you comment some things, Moacir, but I would like to hear
Yeah, yeah. We could
Leo,
start with
Gabriel, Fernando.
Gabriel, which is in masters. We can go like from bottom up.
Yeah. So after you learn the basics, like there are a lot of online courses. Like if you can do like a lot of them, it would help because there are some courses that like the top researchers like the industry like are giving, and maybe you try to apply the it to some problem, some specific problem. Then you're going to realize that in real life, some deep learning has a lot of difficulties for implementing the models. Like you can somehow train our models here and maybe I say I don't know achieve 1 to 5% better accuracy on the I don't know the state of the art, but how that translates to the real world, it's that's very complicated. And if you learn the basics and then you try it out, I'm going to apply this for this specific problem, and you're going to learn a lot probably because a lot of things will go wrong.
So true. Yeah.
Okay,
Leo.
I'll go now in order of, you know.
Okay.
So what I have to say is that you should start small, like really small. So take something that you know works. So don't try to make your own architecture. Don't start from trying to stack layers on top of layers. Just take something you know that works for some domain like text or images, and then approach it from where you want to get. So if you want to do question answering from text, then start getting closer to what you want to do, but never try to solve your problem from scratch. That will very likely not work and it just gets you very frustrated.
Yes, I think to complement what Leo and Gabriel told us, it's if we study the data, it's more easy to understand how the network actually works. So all of us study images. So if we understand how the image process actually works and the filters and noise and so on, it's more easy for to understand how the network can be performed. So we have units that perform filtering, and we can study noise. And an advice is to uh, get some image process methodologies without deep learning to understand, and then bring these concepts to the deep learning.
Nice.
Good.
Marcy, do you want to add something? One
Yeah,
more thing?
well, I'll just add something that's not related to deep learning, but in everything that we want to, that's something that you are starting with. We have to learn how to deal with our own frustrations in the process. So this is very important in any scenario. Although I study a lot of deep learning, I'm quite skeptical about many results. We know that some are quite impressive, but I think we are still to investigate something that can be that go beyond what we have seen in the past 5 years. You see that it's kind of saturated in terms of applications. And I was by chance I was discussing with Erickson from UFMG a few weeks ago. We were talking, and then we were talking about this hype, and especially the students that they they come to us wanting to do something in deep learning. I want to do undergraduate something. I want to do a project on deep learning, and we were talking how this hype can be difficult to solve in terms of how can we explain to someone that's not that easy. And he was saying, oh, it's easy. Just give him some, or her, some real data to work in deep learning. and then I added give him a gun to try to train. Either of the two would result in big frustration, and then you can see that we still have to be very careful when doing research in this type of field. Yeah.
Okay, nice. So I have one more question. I don't know if we have questions on audience. I think I don't know. So, but I have one more question because you anticipate, I think, my question. And what needs to be improved in deep learning for we achieve more big steps now? We don't have a correct answer here.
Yeah, there's no correct answer.
I don't know. I'm asking because I don't know.
Yeah, go ahead, please.
Okay. I think we should start doing small steps. That would be great, because we have loads of stuff that is online and being used by millions of people that is basically untested. And that's really, really dangerous. So I think the big step to take is to slow down and stop deploying stuff. Just do the research first.
I used to say to my students that we need to talk more about ethics than techniques. So because we have a lot of problem on that.
Yeah. Yeah, I think I was mentioning external validation. I think this is something that it appears on medical data, but I'm convinced that we should come up with better ways of evaluating it externally. And then I was thinking of a way of doing it for this tutorial, and I failed because I couldn't find a proper way to build up a external evaluation. I tried to use CIFAR 10 and CIFAR 100 to do that, but it was not convinced. I was not convinced this, and I just dropped it. So maybe this is something that could give us more insight on what's going on. Because if you train a model and then you try to use it in a very similar context, and it doesn't work, then it means there's something wrong. So I think this is one step that evaluation and proper evaluation, I think this would be a good next step to make sure that we are deploying something that's we can trust. Yeah.
Okay. Fernando, Gabriel? No?
No.
Okay, I think we have problem. Oh, Gabriel, sorry.
No, I'm still thinking here.
We have problem on generalization, interpretability, efficacy, and maybe we have to so we have to slow down. I agree with Leo. Yeah.
Yeah, I also guess interpretability is quite an issue that, it's unsolved, and I don't see in the near future being solved like that easy.
Yeah, it's a hard task. Maybe we never solved that for deep learning because we are dealing with neural networks, so we have another.
Yeah.
It's I don't know. We have.
I know a
possibility to solve that.
Yeah, I know a lot of people. Well, some people is working on that.
I'm working on that.
Yeah. You. Yes, I was going to mention that lots of research. I know researchers at Unicamp that are working on that. So not Sandra, but also other people. Barbara, which is here, I think she just commented. I was also working something that's related to how to interpret them and make them better and use unlabeled data and such. So I think always everything contributes to this type of in this direction.
Nice. Let me check if we have some questions. No. So I think we can close the sections.
Yes.
It was a very helpful, it's really very helpful tutorial session about the deep learning from deep neural networks from zero to hero. It's true. It's a good name. And I want to thank you all, the presenters today. I mean, it's really true. When I did, you did an amazing job here. And I would like to thank the audience for taking part of this event today. And so thank you so much. And was the first day of the SIBGRAPI, an amazing day. So thank you, everybody. And I wish you well. So bye-bye. Thank you.
Thank you.
Bye.
Bye.
Thank you. Thank you.
Hi everyone, so you can continue the conversation on Discord, and we expect to see everyone tomorrow for the first technical session. And thank you for all the authors from the tutorial and for Sandra for chairing this session.
Thank you, Gastal.
Bye-bye.
Bye-bye.
See you tomorrow.
See you.
See you.